Today we have Misha. He'll be talking about new directions in algorithms with predictions, learning, and privacy.
Great. Yeah, hopefully everyone got food. Yeah, my name is Misha Khodak. I'll be talking about some new work on algorithms with predictions, which was joint with Karim Amin, Nina Balkan, advic, Amit Tawakar, and Sergey Vasilievsky. So before we get started on new directions, let's discuss what algorithms with predictions actually is. And as we all know, in traditional algorithm design, the goal has generally been to do well on the worst case instance of a problem. But in modern analysis, a lot of people have started moving beyond worst case, and a lot of interesting examples of this have been shown. So in average case analysis, where we want to do well over some distribution over the instances, in smooth analysis, where we want to do well over perturbation of a worst case instance. There's examples in data-driven algorithm design where we learn how to do well from a data set of instances. And then the topic of this talk, which is algorithms with predictions, which asks a question, what can we do if our instances are in some way predictable? And to explain what I mean by this, I'll discuss kind of a canonical example that everyone gives in this field, which is, can we do better in querying a sorted list if we know something about the input? So let's say we have this list of famous authors and we want to find Mark Twain in this sorted list. And what classical algorithm design tells you to do is, of course, binary search, which, as you all know, has a runtime order log n, where n is the size of the list. But what would you do in this case if you had this issue in a library? What you would do is you would know that t is 75% of the way down the list. So we're not going to start in the middle and recurse. We're going to start 75% of the way down the list and maybe recurse from there. That's what we would do as humans, and you can encode this algorithmically as well. If you have a predicted index w that's in the size of your list, then you can get a span containing both w and the true index that you know for sure contains it using doubling. And then after you have this span, and the span is going to be roughly of size order w minus order the distance between your prediction and the true index, you can then binary search on the span, which of course will also have runtime of log the error in your prediction. So in total, we've now cut down our runtime from log n to log the error of your prediction. And in this case, we just kind of did this naive approach where we went 75% of the way down the list. But if you're smarter, or if you're a machine that's done some learning, you'll know actually that the distribution of last names is skewed, and that actually t is going to appear somewhere 90% of the way down the list. So you can actually start here, for example. You don't have to start 75% of the way down the list. And so with this motivating example, what actually is algorithms with predictions? The goal here is we want to design algorithms that can take advantage of a prediction W to improve the cost of running on some instance X of the algorithm, and we'll call the cost Cx of W. And the generic guarantee that we see in this field is that we want to find a function Ux of W that bounds the cost of running our algorithm, and we want Ux of W to be small if the prediction is good. And ideally, it's going to circumvent worst case lower bounds, and we call this consistency. And we also want it to be not much worse than the optimal worst case cost, and we call this robustness to say bad predictions. And in our example before, we had the upper bound was log of the error in your prediction, so the difference between W and the predicted index. And of course, that cost is at most log n. So up to constant factors, we don't do much worse than the worst case algorithm. And there's been many new algorithms for predictions that have been constructed in recent years. And this rapid development has been spurred by a combination of empirical success. So actually, one could say this whole sorted thing was started from the systems community, and there's now been developments on top of the original papers, with Microsoft constructing very kind of advanced systems for learned indices. And also just as an exciting area and practical area of beyond worst case analysis. So for example, it appears as a chapter in the recent book by Tim Roughgarden. And the area covered by these algorithms, and I'm sure I'm missing quite a few applications, but these are some of the example problems that have been provided with algorithms and predictions that do well if we have some prediction about the outcome of running the algorithm on an instance. But there remains one question, which is the first question we're going to answer in this talk, and that is, how do we obtain predictions? And there's been some results that bound the sample complexity of learning a fixed prediction from IID instances. So if we have a bunch of instances drawn from some distribution, we can learn the function, we can learn the prediction that does best compared to the upper bound UX of W on the cost of running the instance. And these are some of the example problems that have been provided these sample complexity guarantees. But even with those, we don't really have results for if the instances are adversarial and we have to solve them sequentially, which is an important application. And we also don't have results if we want an instance-dependent predictor of W. So for example, in the sorted list example, the existing predictions would basically say always start at a fixed point. So maybe the median of your distribution, just always start there for whatever query you're given. And of course, you know, the example I gave before depended on the query T. You want instance-dependent prediction of your query rather than just start it at the middle of the instance. And so we want our predictors to both depend on the instance, we want to be able to solve them sequentially, and we want kind of a more generally applicable approach to finding predictions that can be learned, and so we can apply them to more problems than have been highlighted. Yes.
So I'm not completely clear on what the two types of information that we're learning off of. So you said that these existing approaches don't learn anything, don't use the.
They don't use the instance, but they do use the outcome of the prediction. So for example, if you have a distribution over last names, the optimal thing to do isn't start at the middle, right? It's start at the median of this distribution. And that's kind of what you learn. You learn a fixed thing to do for any instance that you're given. Here, the instance is the last name, and you do the same thing for every last name, but that thing isn't necessarily start in the middle. It's start at, say, the median of the distribution.
Okay, and then what we'd rather do, the more advanced approach would be sort of a different point for every last name.
Right, yeah. And so the first direction that we're going to discuss in this talk, which is appeared in a paper at NERP 2022 with Nina, Amit, and Sergey, is we introduce a framework for proving learning guarantees for algorithms of predictions. And specifically, the framework improves on several sample complexity results and yields new ones. It provides lower grade algorithms against adversarial instances. And also, it easily extends to at least a linear prediction setting. So if we want to learn a linear map from the instance to the prediction, we can handle this case using this framework. And the second question that we ask in this talk is, can we use predictions beyond traditional areas of algorithm design? So what these questions have covered is, can we use predictions to improve costs that are something like time complexity or communication complexity or competitive ratios in online algorithms? And the second question we consider in this talk is, what about other types of costs? And specifically, we're going to focus on improving error due to differential privacy. And this is joint work with Karim, Travis, and Sergey. And here we design algorithms with predictions for 4 important new differential privacy applications. We provide algorithms with predictions for them. The benefit of this analysis is that it has minimal assumptions to past differential privacy work that incorporates external information that we might want to use. And we also extend our learning framework from the first part to yield both sample complexity and regret bounds for all of these applications. So as an outline of this talk, what we're going to do is, in part 1, I'll discuss the new framework we have for learning predictions. I'll overview what we actually, how you might want to do it if you have new problems that you want to apply it to. And I'll apply it to 2 interesting examples, which is to bipartite matching and to online page migration. And in the second part of the talk, I'll go over the private algorithms of predictions application. I'll give an example on how we design an algorithm with predictions for private covariance estimation. And I'll extend our learning framework to handle also both this covariance estimation case and any other private algorithm with prediction we might want. And I'll explain why we actually have to do some work to extend it at the time. So before I get into the first part, are there any questions? Okay, great. So the framework we're going to be working in for algorithms with predictions and the learning aspect of it is in online learning. And here the setup is, say we see a sequence of adversarially given instances, which are indexed by T1 through big T. And our goal is to learn a low regret prediction WT, so it's going to be fixed for now, given the previous predictions and the previous instances, so as to minimize the regret, which is the upper bound on the cost of these predictions. So specifically, we want compared to the optimal prediction in hindsight W, we want the regret to be sublinear. So the sum of our losses of our actual predictions to be small compared to a fixed prediction in hindsight. And this is a standard setup in online learning. And the reason we might want to do this is it bounds the average cost. So the average cost CW of running the algorithm on the sequence of instances. It bounds it by some term that's little o of 1, right, if we divide by t, and plus some minimum over the average upper bound on these costs. Yes?
So to be clear, we're only trying to have low regret versus an adversary, which is only allowed to have a fixed prediction for all time steps.
Yes, right now. I'll get to, yeah. We also, we want to do this one because, yeah, it gives us a bound on this average cost. We want to handle non-ID data in some applications where the data really is not given to us as like one fixed data set, but we somehow see it sequentially over time. There are many efficient online learning algorithms to choose from so that we can customize our algorithms to specific applications and get better regret guarantees, get better sample complexity guarantees, and so on. And then there's an easy conversion to, as I said, sample complexity guarantees from these online learning algorithms that we'll see actually improves upon sample complexity results in algorithms with predictions from the past. Okay, and so there's two steps really here to the framework. And the first step is to derive a quote unquote nice upper bound U of X on C of X. And really the argument I'm going to make in this talk is that U of X should be seen as a surrogate loss for the cost of running this algorithm on the instance X. So if you're familiar with more standard notions in machine learning, oftentimes in, say, classification, we want to bound the 0-1 loss. So it's just 1 if we made the incorrect prediction in classification and 0 otherwise, but we never actually optimize this 0-1 loss algorithmically. What we actually do is we optimize some surrogate loss and hope or prove that this is just as good as optimizing the 0-1 loss. And my argument here is that we should treat these upper bounds that we are already deriving U of X in algorithms predictions with the same idea. And specifically, we want to have some nice properties. It doesn't have to have all of them, but it certainly would be nice if you have all of them, or you have to work around the ones it doesn't have. So maybe we want it to be convex, just like these surrogate losses. We want the domain to be convex, and we want some type of regularity, of course, like Lipschitz. And the second step really is to apply online learning and existing online convex optimization guarantees to get everything we want, which is low regret, sample complexity bounds, guarantees for instance-dependent predictors, as I'll get into, and so on. And as I said before, you get these efficient problem-specific learning algorithms using this approach. And the reason why you might want to use this framework can be seen through a comparison between what people have done in the past in algorithms predictions and what I'm proposing that we should do when you want to derive learning guarantees for predictions. So in the past, what people really do is they derive this upper bound UX of W on the cost of running your algorithm with predictions. And then you do one of two things. Either you kind of give up there and say, oh, I guess we can't learn this. And really what you're saying is that if you have some notion of similarity between your prediction and the true output of the algorithm, then you'll do better, but you don't have any kind of guarantee of how you can obtain this prediction. So that's one outcome. Or you do some work, often using empirical risk minimization, so minimizing just the average upper bound over all your instances. You do some VC dimension or pseudo dimension type analysis, and you get a sample complexity bound. And what I'm proposing to do in this framework is you do the same thing as before at the first step. You derive an upper bound. You do a little bit more work to make the upper bound nice, and I'll show what this work entails in our examples. And then you apply online learning on these upper bounds to get a lot more things. You get sample complexity as before, but you also get lower regret guarantees. You get at least some guarantees for instance-dependent predictions, and the algorithms are by design practical and efficient, at least in most cases. One other thing I would like to point out here is that this framework really emphasizes giving a bit more effort to what kind of algorithm designers are already good at, which is kind of upper bounding the costs on running these algorithms. So do a bit more effort on the actual algorithms prediction part to make the upper bound nice. Once you've done this, online learning gives you a lot of benefits that haven't been realized before, but which I'll show you get later. So this is the overview of what I'm going to do. I'm going to go into 2 examples now. Are there any questions for now? Okay, so let's start with an easier example, not easy in terms of the algorithm predictions. Much of that has actually been done before, but really easy in terms of what we have to do to make the upper bound nice and then to apply online learning. And the question here is this question of faster matching using learned duals. And here the problem is, say we have a bipartite graph. The graph has m edges and vertices, and we want to find the perfect matching with least weight according to the edge weights. And the edge weights are denoted by c, and it's their integral, so they're integer. It's an integer vector, m-dimensional integer vector. And so in NeurIPS last year, there was a proposed algorithm with predictions. So if you have a prediction W of some aspect of the problem, which is the duals of the problem, you can run a warm-started version of the kind of the well-known Hungarian method for solving this problem. And what this really is a primal dual scheme where the duals are initialized at W, and the scheme has runtime order m squared n times the L1 distance between your predicted duals W and the actual ground truth duals, which you get at the end of running Hungarian on this instance. And the ground truth duals are, I'm going to denote y star of C. So they depend on the edge weight C, and C here is kind of the instance. So this is what's been done before. And what that paper also showed is that you have a sample complexity of actually learning this prediction W, which is roughly n cubed over epsilon squared. And basically this is enough. This is how many instances you need to learn a fixed predictor W, such that with high probability, the error in expectation over the distribution over the instances that you got samples from is only epsilon suboptimal compared to the best predictor over that distribution. And here, the upper bound that was derived is this L1 distance between the duals that you're predicting and the ground truth duals output by Hungarian. Okay, so we have this setup. We have an algorithm with predictions, and we have a sample complexity guarantee. And so we can start looking at that algorithm with prediction, and specifically the function, the upper bound that was derived previously. So we see this upper bound as an L1 norm, L1 distance between what we're trying to predict and some vector that we have. And this already seems kind of nice, right? Why don't we apply, online gradient descent? So just a gradient-based algorithm to these upper bounds. And the issue really is that these W's are integral. So they're integer vectors in z to the n, where n is the number of nodes. And so we can't directly apply online gradient descent because we have to project first from the real vectors where we want to actually run online gradient descent. It's a real algorithm to the integers. And on the next slide, I'm going to show how we're going to do that. But the first result in our work is we show that you can project from just a very basic projection of rounding from the prediction from a real prediction W to an integer prediction tilde W. If you initialize the primal dual scheme from that, you get the same runtime, basically up to a factor 2 approximation. But what you also get is a regret guarantee. So you get a regret guarantee that says the regret with respect to the optimal prediction in hindsight is C times n, and it's the number of nodes, square root 2t, which is the sublinear regret you want in online learning. And you also shave off an n log n factor in the sample complexity, basically directly by online to batch conversion. I won't really get into online to batch conversion much in this talk, but that's kind of what you can do. So there remains a question really of how do we project W, and can we show actually that this projection preserves the distance to y star C. So this is step 1 of our framework. We want to get a nice upper bound. And to do this, we want to show that for any real vector W over which we're running online gradient descent, we're going to round it to a vector tilde W in the integers, n-dimensional integer vector. And then for any n-dimensional integer vector y that's different, we're going to show that the rounding is less than 2 times the original distance. And so the proof here goes as follows. We let S be the set of indices from 1 to n, where basically the y vector is in the same direction as the rounding. So if y is greater than w and the rounding goes up, or y is less than w and the rounding goes down. And we want to show some facts about this. So in this cartoon, kind of this is, say, the real line for any index. And so in the first case, where I is in S, so in case where this holds, and y is on the same side of w as its rounding, we know that basically the distance between y and w is just the distance between y and tilde w plus the distance between tilde w and y. So we know that this summation holds. And then if you just get rid of this term, then we know that it's greater than y is greater than y minus w tilde. And then the same kind of thing holds if actually it's the opposite case where y is bigger than w. And then for the indices where it's not in the set S, so where y is actually on the other side of the rounding, then we know that y is actually greater than 1/2. Because like this distance must be greater than 1/2, otherwise we would have rounded here. And then this is of course also greater than this distance. And so therefore we can do a fairly simple calculation. We separate the L1 norm into indices in S and not in S. And then we upper bound it by fact 1. So the first upper bound just follows by the first fact. And the second is triangle inequality. And then what we're going to do is get rid of this term by upper bounding it by the same term here. And this follows by fact 2. And so now we have just 2 times this term. And then we recombine terms and we get that this is upper bounded by 2 times the distance between the original real vector and the learned duals. And kind of what's critical here is that we know that y is an integer vector because we know that the solutions to Hungarian will always be integers. If y was not an integer vector, then this might not hold because y could be like here. Okay, and for step 2, we're going to apply online learning. And as I said before, this is really the part that you really let machine learning do its thing. And we're going to apply kind of the simplest online learning algorithm, which is online gradient descent. What online gradient descent is at a fixed point, you have a learning rate or step size eta, and you subtract from your current point the gradient with respect to the upper bound that you're interested in, and you project it to, right now we're going to focus on online optimization over the L infinity ball. And so following from kind of very standard regret bounds, you get the regret result we wanted, which is basically order n times the square t, which is sublinear in t, which is what we want. Then you can do online to batch conversion. Basically what you do here is you do some, you take the average of the, if you assume that all of your instances were drawn ID that you did online learning over, you take the average instance, or you take the average prediction that you had over your entire runtime. And in a very classical result, you can show using basically martingale analysis, you can show that if you have enough samples, so n squared over epsilon squared samples here, you can actually get an epsilon suboptimal prediction for your distribution. And as I mentioned before, this shaves off an n log n factor from the original sample complexity of learning the integer dual. And the extension here to learning mapping from, say, an f-dimensional instance feature to prediction. So this is the instance-dependent prediction I was discussing. Really comes from if you have a convex function of w, it implies that the convex function of the map A times the feature vector is also convex in A. And so you can learn A in the same exact way as you learn W here. You're going to run online gradient descent on the upper bounds, and then you're going to take the average A for sample complexity. And so online gradient descent is going to have regret C times n times f, where f is the dimension of the feature of each instance. So to summarize this first result, what we've showed is approximately an order n improvement in sample complexity, plus online learning guarantees. And all of this was done with a 3 times shorter proof. So this is our proof, and this is the original proof. This is just for learning, and this includes not just the learning proof, but also the upper bound on the 2 approximation to the L1 distance. This is, of course, not a rigorous analysis. Maybe I was denser with my wording. But the point I'm trying to make is really I'm trying to make the learning of these predictions easier for everyone to do. Just focus a bit more on making a nice upper bound and just apply online learning. You'll get stuff for free. We also do an easy extension to what this paper also did, which was B matching, and of course the learning of linear predictors. A similar analysis also gives an order n squared better sample complexity than previous work in a more recent paper. So in a recent paper at ICML 2022, there were some extensions of this paper to other graph algorithms variations, such as single source shortest path. And you can apply, again, online learning to do better, get better sample complexity in that case. And even more recently, our framework has been applied to even newer results with even better regret guarantees by some other people. So they applied our work to bipartite matching, to a weighted matroid intersection, and to a discrete energy minimization. This is a problem in computer vision that they studied. Yes.
So this really long proof is the right way to interpret this is that they're demanding you're doing ERM. That's maybe a very hard thing to maybe you're overfitting samples, and that's why you suffer this loss in sample. Whereas you're saying we don't need to do ERM or something that strong on the samples to relax that a little bit. So online gradient descent maybe is not going to find the best thing on those samples, but it's going to have a much better sample complexity guarantee, and then you're around things as well.
Of course. Of course, that's true. Yes. So online gradient descent these are I'm saying we do better in sampling complexity, but I do better sampling complexity for different algorithms, kind of as you point out. I'm giving you a fixed prediction, whereas ERM guarantees say usually it's uniform convergence. So every prediction will have some generalization gap, and so the optimal will be good. And maybe that's why the proof is hard. Really, I think it's working with pseudo dimension, which is what this proof uses, is kind of hard. And I think this is why it took a while. I don't know if there's like a difficulty of learning to difficulty of proofs kind of analogy that you can definitely make. Maybe. Okay, so I'm going to move on to a slightly more involved example, which is online page immigration with learned advice. And so here the problem is pretty different. Here we have a finite metric space K, and we have some server that's getting requests, so a sequence of n requests from this finite metric space. And the server has a state which is also a point in the metric space, and it maintains a state at each time step n, or each time step in n. And at each time step, it can move to a new state at some cost, which is c times the distance between those new states. And it also has to fulfill this request that it's given, so the sequence of requests at cost, which is the metric. And so in AIStats 2022, there was an algorithm introduced for doing this if you had a predicted sequence S hat of the actual sequence S. And what the algorithm says to do is use the offline optimal for S hat, which you can compute, but you're only allowed to move on multiples of K. Where K is some parameter, ideally we could learn it. I'm not going to discuss how to learn it. I'm just going to treat K as some fixed thing, but it's a parameter of the algorithm's prediction that they introduce. But basically, yeah, you do the offline optimal for S hat, but you only move on multiples of K, where K is an integer less than n. And the guarantee they have is on the competitive ratio. So the cost compared to the optimal is going to be, roughly speaking, 1 plus this thing, which is basically the average over K of them. So the maximum number of errors in any K interval of your sequence between the predicted sequence S hat and the true sequence S. So, this could be at most 1 if everything is wrong in some subsequence of n, or it could be much smaller if in all subsequences you're pretty good. And so now let's think about this. What can we do here? Well, we can learn a categorical distribution W for each index I equals 1 through n. So each of these is basically a distribution over the metric space. And that's what we might try to do first. And so what we're going to do is instead have an expectation of the cost. And we're going to sample at each time step in S hat from W. And so now we have kind of an upper bound, but it's going to be an expectation. Unfortunately, this is non-convex. I don't really know how to compute this actually, like how to make this kind of a closed form in W. And so we're going to have to do some more work to make this upper bound. And also I should say this is kind of a very weird and annoying learning problem because we have to learn over an entire metric space and over every sequence in that metric space. We do have results for kind of an autoregressive setup where you have a smaller matrix A that learns from the previous states, and you don't have to learn a full categorical distribution over every request in your instance. But for now, I'm going to consider this simple case. Okay, so so we have this annoying upper bound on the expected cost, and what we're going to show, and I'm really only going to give a sketch, is that it's upper bounded by this thing, which is log n plus the maximum of the expectation of the errors between the predicted sequence and the true sequence. So basically what I'm doing here is I'm just moving the expectation inside the maximum. And the reason I want to do this is because the maximum of convex functions, which this is, it's 1 minus a linear function, is convex. And E here just denotes the one hot vector which is 1 at the position at time j in the metric space. And here the sketch is, each of these random variables inside the summation or inside the expectation, it's a Poisson binomial. You can use its moment generating function to show that there is some concave increasing function. It's 0 at if the expectation is 0, or the maximum expectation is 0. But also the expectation of the maximum is an increasing function of the maximum of the expectation. Unfortunately, this function is annoying, so we're going to upper bound f by its linear approximation to get the result. And the sketch here is what these functions of the maximum of the expectation look like is that they rise sharply here and then are kind of linear. So we're going to upper bound it by its linear expectation. You can view this log as the error you obtain here. And then your expectation goes, and then the rest of the function is fairly linear. So you do suffer here, but it's only logarithmic in them. Okay, and so now we're going to do the same or similar thing as before. So we have this upper bound on the cost. It's log n. It's upper bounded by 1 plus log n over k, or upper bound on the expected competitive ratio. It's upper bounded by log n over k plus this convex function. So here we do need kind of that log n is smaller than k, otherwise this is not too interesting. And so we have this nice upper bound, but now we're actually learning over simplices, so it is convex and we could apply online gradient descent, but it's more optimal. And as I mentioned before, this kind of framework allows you to do custom things for different algorithms and predictions. So we're going to actually do exponentiated gradient descent here. Because what it gives you is regret that's logarithmic in the size of your metric space, which is important in this application. And then again, you get an exponentiated gradient basically multiplies each current categorical distribution by the exponent of the negative gradient with respect to your current loss function. It's similar to multiplicative weights. And then what you're going to get in terms of regret is an upper bound that's k, which is a parameter of the algorithm, times n, which is the number of time steps, times t times log of, or squared t times a log of the metric space. And you can get sample complexity as before using online to that conversion. And you can also get linear prediction from instance feature here. It's more complicated because the output space has to be a simplex, but you can basically use stochastic matrices to get this done. And here, as I want to emphasize, you have this cost upper bound. You have the learning algorithm, and you have the learning guarantees. This is kind of the steps of a framework that I suggest you do if you ever end up working in algorithms for predictions. What you want to do is you want to derive some cost upper bound, you want to apply an online learning algorithm, and then you'll get all the stuff that you want. So the key takeaways I want to emphasize about learning in this talk is that guarantees for algorithms with predictions should be not only robust and consistent, as I mentioned at the beginning, but they should also be learnable. They should also be in some form that you can actually apply a learning algorithm that you might want to use in practice to get predictions that you can learn. And this kind of establishes end-to-end guarantees, so both computation and learning for algorithm predictions. And it's critical for practical applications with more complex predictors, such as neural networks, because in practice for neural networks, say we're going to run some version of online gradient descent. And so our framework is a guide for how to do this. What you want to do is derive a nice upper bound on the cost, and then apply online learning. And in addition to the results I had, we have numerous new and improved learning guarantees for existing algorithms. So matching and some other graph algorithms, page migration, job scheduling, and ski rental. And so we have these results for existing algorithms. And what I'm going to show up next is, what if we want to move to a new area? We want to design algorithms predictions for that area. And we want to apply these learning framework to upper bounding costs on differential privacy. So before I go there, are there any more questions? Yes.
So this sort of cost function, are we thinking of this as the cost for misprediction for a single misprediction, or the cost for like making this mix? There are some scenarios where the costs, where you sort of get a loss from each misprediction you make.
Mm-hmm.
There are other scenarios where it's sort of like most of your loss comes from like accumulating, having a whole bunch of mispredictions across all your different.
Right, like an online setting.
Sure.
Yeah.
Does this, when you say a nice upper bound for the cost, is it a nice upper bound for the cost in terms of like the misprediction, the per element misprediction, or the sort of global misprediction?
Here, I'm really discussing the global misprediction, because it's not really a misprediction. Here, I'm just saying, what is your performance measure? Upper bound that by you. So it's not like I don't know if I would call it like a cost of misprediction. I would just call it the cost of running your algorithm.
But as in, it's the cost of, if I use this prediction or this like matrix that takes features to whatever, for every step, what would my prediction amount be?
Yes. Okay, so I'm going to move on to differential privacy, and to do that, I want to make sure that everyone understands what we're talking about. So as a recap, some basic definitions here are that we want to construct an algorithm that goes from some input space X to an output space S, and we say that this algorithm is epsilon dp, or epsilon differentially private. If for all neighboring data sets in this space, we have the probability of it being in some output is smaller than the probability that the neighboring set is also in that output, up to some multiplicative factor, which is e to the epsilon. And we say data sets X and X tilde are neighbors, and this depends on your definition, but we're going to use swap for this talk, is basically obtained by swapping a single data point from one data set to the other. And so the example here from our sorted list is if you have this list and then you swap out Swift for Twain. And the cartoon here is that if you run this algorithm A on, or if you run one algorithm A on one of these data sets and you output an answer, an adversary has no way of knowing, up to some probability, which data set you ran your algorithm on. And the generic guarantee that you get in this field is that an algorithm is epsilon differentially private, and the error of your algorithm that you run on X is some polynomial of 1 over epsilon and log 1 over beta, where beta is the probability of failure. I'm also going to discuss a bit about composition. So if an algorithm is epsilon dp and another algorithm is epsilon prime dp, then you can compose these two algorithms and you can compose the differentially private guarantees additively. And the common mechanism that people use here is basically add noise to your outputs or have a bunch of different steps at each of which you add noise to your outputs. And usually this takes the form of something like the algorithm is what you want to output plus some Laplace distribution that depends on how sensitive your error is to your noise, to changing data sets from x to x tilde, divided by the level of privacy you want, which is epsilon. And so what you end up getting is you want to make sure the adversary can't distinguish between basically adding these two distributions. So this is what a Laplace distribution looks like basically. Are there any questions about epsilon differential privacy? Okay, so why do we want to use external information, which in our case is predictions, in differentially private algorithms? So we have a lot of external data that we might want to use in these algorithms. So for example, large public data sets, such as a census data set or Twitter. In other cases, we might have many related sensitive data sets. So for example, cell phones, and we're some cloud provider that has access to data on these cell phones, but we want to output something for these cell phones like models that are private to each individual user. And why might we want to use this external data? Well, it often doesn't hurt privacy, for example, if it's a large public data set. And also, we might have a lot of this data, and in differential privacy, you're really kind of constrained to how well you can do by the amount of data you have and the privacy you can tolerate. So if you want to actually do better, the real only thing you can do, you can either improve your epsilon, your differential privacy algorithm, which might be hard. People have worked on this for a long time, or you can find some external data. And of course, there have been a lot of applications where people have incorporated external information into predictions. So this has been done for the setting of data release, for mean estimation, and for a lot of things in machine learning. So these analyses didn't treat this as an algorithms predictions problem, and I think we should. And the reason I think we should is threefold. So one is that algorithms with predictions is kind of designed to have very minimal assumptions. Whereas past work really assumes pretty strong assumptions on the distribution of the data, either the source or the target data comes from, its IID, and often it's Gaussian or something else. We really have minimal assumptions on top of the original algorithm. We also have a natural way of talking about robustness to noisy predictions. So in past work, there's often no fallback option if you have a really bad prediction. And for our case, differential or algorithms predictions has these standard techniques for trading off robustness and consistency. I won't really discuss this much in this talk, but this is kind of a very useful thing in practice. And then, of course, now that we have this framework, we have a way of learning these predictions. So in the past, what people assume is really that you have a fixed source of data, often just a large public data set, and all this external information comes from the single public data set, and now use this data to run your new algorithm. And what our learning framework allows us to do is, instead of having a fixed public data set, you can also have kind of the cell phone example I had before, where you have a bunch of small data sets that you want to learn from. They're all sensitive. And how do you learn a prediction if you have a bunch of sensitive data sets instead of one single public data set? Okay, and so I'll go into an example here, which is the example of private covariance estimation. So here, the goal is, say we have a data set. It's a data set of n entries, so n users that we want to maintain privacy with respect towards. And each of them have a d-dimensional vector, and we want to return a private estimate of the covariance matrix of this data set, which is just 1 over n, and it's the number of users, times xx transpose. And we want the Frobenius error of this DP estimate to be small. And so the state of the art here, which is actually in NeurIPS 2022, is called separate cov, or separate covariance. And it's kind of a very simple algorithm. It's kind of odd, but what they do is they first estimate the eigenvalues of the true covariance matrix C, and then they add noise to it. Then what they're going to do is they're going to estimate the eigenvectors of a different matrix, which is the original matrix C plus noise. And this is also Laplace noise. This is should be symmetric, but it is, that's what they're going to do. And then they're going to add noise to the original covariance, and then they're going to take its eigenvectors. And then what they're going to output is kind of the recombination of this, which is U times, which is the eigenvectors, basically the eigen decomposition. And then they provide this guarantee, which is if X has unit norm columns, then, so each user basically only provides a column that has unit norm, then this algorithm, Seprakov, is epsilon differentially private. And with high probability, you get a bound on the matrix its output, the Frobenius norm squared distance between the matrix it outputs and the true matrix. And it's going to depend on basically a fast term in n. So it decays as n squared and it only has d in the numerator. And then a slow term, which is d root d over n, and also has and also depends on the trace of the matrix. So the trace of the covariance matrix. And so now, if we think about this and say I have some symmetric prediction matrix W of C. The idea here is kind of very simple. What if instead of running the algorithm on C, I run it on C minus W? So I compute the eigenvalues of C minus W, add noise, and get some noised eigenvalues. I do the same thing with the eigenvectors, and then I recombine them. And then at the end, I'm going to add W to the result because I estimated C minus W with U lambda U transpose, and so I need to add W back. And the hope I have here is that I'm going to replace the trace norm of C with the trace norm of C minus W. And what's nice about this is if my prediction is good, the trace norm of C minus W is small. And the answer here is yes, we can actually do this. So we have an algorithm called Seprakov with predictions. We do exactly what I outlined before. We estimate the eigenvalues of C minus W and add noise. Or compute them and add noise. We estimate the eigenvectors of C minus W. And then what we're going to return is U lambda U transpose plus W. And the guarantee we have is that Seprakov with predictions has a squared Frobenius error smaller than C minus W trace norm. And some notes here are that basically the observation here is that the original method is implicitly using W equals 0 as its kind of prediction, which maybe isn't the most natural thing you want to do for a zero covariance. You might even maybe even a Gaussian covariance might be better. And our proof for this result basically extends the original analysis, but let's say we have to handle the negative spectrum now, right? In the original case, we only had positive eigenvalues. Here we have to have negative eigenvalues again, so you have to do a two-sided analysis. But on the other hand, our method is also as efficient as before, up to matrix additions. The hard part here is you have to do two eigen decompositions, so we're not really adding any complexity. And we are also crucially for DP, even though it's really constant factors in the result, is we actually are adding the same amount of noise as before. And also, this approach outperforms maybe the first thing you might think of when you want to do an algorithm with prediction for covariance estimation. The first thing you might want to do is, okay, I have this prediction, why don't I output the prediction, right? And that's going to give you an error that's just W minus C Frobenius norm. And as long as n is not too small, so that this term is small, and this term is small, this is going to do better than that because, of course, W minus C is not decreasing in n. Okay, are there any questions about this covariance matrix result? Yes, sorry.
So does W also have to be epsilon differentially private?
No. For now, no. For now, I'm just assuming W is given to you magically.
I have a dumb question. Why don't we just set W equal to C? Then this term at the bottom just goes away, right?
Well, no. Okay, W has to depend on public information, and C is private information.
Okay.
Yeah.
So in practice, your W can be think about the covariance in the public data set. Use that to improve your private covariance.
Exactly. So if we want to compare two past approaches to using external information, yeah, what you would do here is you would set W to be the covariance matrix of a large public data set, and then you would use that as input to this algorithm, and then you would hope that the public data that this is small compared to your private to the covariance matrix of your private data set. Exactly. Thanks. Okay, and the last topic is, what do we want to do if we want to learn these predictions? If we want to learn W, we don't have a large public data set, we just have a bunch of small sensitive data sets. So as we saw, we have this upper bound on the cost of running this algorithm with predictions, which is this trace distance. And this is a nice upper bound in the same sense that as we've been discussing before. So, let's just run online gradient descent, I guess. But the answer here is, if you have a sequence of sensitive data sets that these upper bounds depend on, x1 through xt, you can't just do this because now W is not private. Or now W is sensitive because it depends on these private data sets that you want to maintain privacy for. And so W won't be secure if XTs are sensitive. And here, what comes to the rescue is private online learning, which has also been a heavily studied area, where we have low regret algorithms whose predictions W1 through WT, so all of the predictions over the sequence are simultaneously approximately epsilon differentially or epsilon prime differentially private with respect to swapping out any of these data sets. So you can get rid of the entire data set, swap it out for a different neighbor, and your prediction will be epsilon DP. So it's actually kind of a harder or a stronger notion of privacy because you're not swapping out an individual row in X, you're swapping out the entire data set. And so now what we can do is we can assign part of the privacy budget. Remember, I talked about composition. We can assign part of the privacy budget to learning the predictions, so epsilon prime, and we can assign part of the privacy budget to actually running the DP algorithm on each task, and that will be epsilon. And then at the end, we're just going to add them, and that's going to be our privacy guarantee. And as our last contribution here, the first thing you might want to do is apply the very kind of standard workhorse DP online learning algorithm. So the latest version of this is DP-FTRL. And this is roughly online gradient descent with noise added in a clever way. And the regret guarantee here is going to be dt, d is the dimension of the covariance matrix, and then t is the time horizon, and then times 1 plus d over epsilon prime, so our privacy guarantee, and then the square root of that. And in this work, we introduce a better algorithm, and specifically it's non-Euclidean DP-FTRL. And roughly what this is instead of gradient descent, it's online mirror descent with a clever way of adding noise, same way. And this is the first online learning method that we are aware of that can use any regularizer to adapt online learning to different geometries, at least in privacy. And here, instead of using DP-FTRL, if we use a Shat and P-norm regularizer for P set correctly, then what we're going to get is regret that shaves off a square root D factor. And when we go to sample complexity and we do online to batch conversion, what this gets you is a D factor better sample complexity as well than applying the regular FTRL algorithm. Yes. D is the dimension of the covariance matrix. So I'm applying this to the covariance matrix problem. But this method also improves learning guarantees in in all the other DP applications we study. It also improves those learning guarantees. Okay, so as an overview, we design these differentially private algorithms for a bunch of different cases, not just covariance matrix estimation. It's also quantile estimation, where we have these upper bounds that are kind of these negative log of the integral between a prior prediction on the quantiles and a distribution induced by the DP mechanism. We have covariance estimation, as I discussed, and also to do the data release setting, where we're trying to release a data set or try to release a sanitized version of a sensitive data set. So we have a data set of counts here, and our upper bound is just the KL divergence between categorical distribution of these prediction of these counts. And all of these come with robustness guarantees and efficient methods of learning predictions based on our non-Euclidean DP-FTRL algorithm. And as part of this, we also have some results of independent interest, as I mentioned, that learning algorithm. And also for quantile estimation, by analyzing predictions, we also get the first algorithm for quantile estimation that doesn't assume the data is bounded on the real line, say. And the
data is not bounded, how do you do that?
So here, because it's quantile estimation, the sensitivity of the data isn't unbounded because the error is at most n, right? This kind of depends on the cost metric we're interested in for quantile estimation, which isn't a distance metric. It's how many data points is the error. So the error is at most n here. And that's the reason we can basically use a prior that's not just a uniform distribution over a bounded interval. In fact, we actually use a Cauchy prior here. So it's kind of an interesting application of like a Cauchy distribution. Okay, so the key takeaways from this talk is in the first part, for learning with predictions, I believe that you should design algorithms with predictions that have learnable guarantees. And our framework helps us to do this. And it provides a lot of new and improved learning guarantees for algorithms with predictions. And then we, of course, have a lot of open questions, which is, can we co-design algorithmic and learning guarantees based on this? And can we characterize the suboptimality of the upper bounds on the cost that we are exploiting? So we are optimizing these upper bounds. The cost might be much smaller, and we're not really optimizing the optimal prediction for the cost, but for the upper bounds. We should really think of how suboptimal are these upper bounds that we're deriving in algorithms predictions, maybe from a learning perspective, maybe from a computational perspective. And the second part, I introduced some new algorithms predictions for improving the error due to privacy. And the advantages here were that it had minimal assumptions, it had robustness, and it had private learnability. And open questions really is that for some specific problems, is that we want some nicer quality metrics, UX, and this kind of gets more into the details of the paper, but we want to consider better guarantees for specific multiple quantile estimation. And then, of course, there's differential privacy is a huge field. There might be numerous applications that could incorporate predictions. More broadly, are there other cost metrics beyond privacy, beyond time complexity, beyond communication complexity, beyond competitive ratios that we could apply this to? Can we improve the mixing time using predictions? Something like this. So thank you everyone for coming and for staying over. I know we started a bit late. Yeah, my website is here and the papers can be accessed here on the archive. And of course, email me also. Thank you.
Yeah, let's take this again.